Okay, welcome to the today's class. We have covered the portion till time was about the different attachments to the cycle and working with the examples associated with those ideal or non-ideal components. Now in today's class we are going to see some aspects of the cycle. What aspects we have seen till time? The aspect what we have seen was that what is the Brayton cycle upon which we can have our power plant running. And then we have seen that if this Brayton cycle operates, then what are the governing parameters of that Brayton cycle, means how the performance of the given Brayton cycle gets altered. So we have seen that performance of the Brayton cycle gets affected by working medium, gets affected by pressure ratio. So these are the two important things which are there for the ideal cycle also. Further, there is performance alteration with other attachments, like if we have heat exchanger, if we have reheater, and if we have the intercooler. So these things will alter the performance. What do we mean here by performance? Here performance by the meaning of ours is related with the efficiency of the plant, and then the efficiency, what did we talk about was the thermal efficiency of the power plant, which is net work upon Q in, which is rather Q out minus Q in upon Q in. That was the overall efficiency, rather that was the thermal efficiency of the power plant. That is what we had seen. So the point is for the other components, for the components like reheater, we have considered that was not rather mainly for increasing the efficiency, but that was for increasing the power output of the power plant. And then we have considered exclusively the heat exchanger for the concept of increasing the efficiency. So these are the things what we have already thought about. But then what we had thought was that if these components are non-ideal, then there are isentropic efficiencies associated with turbine, associated with compressor, then there is heat loss with the heat exchanger, and all these losses would lead to different efficiency than the efficiency which we have calculated otherwise, considering everything to be ideal. So the performance of the cycle gets altered by pressure ratio and by gamma in case of ideal cycle, and performance of the cycle gets altered by same RP, same gamma, but along with the compressor isentropic efficiency of compressor, isentropic efficiency of turbine, and then the losses in the heat exchanger or combustion chamber. So these are the things which we have seen. But all these things whatever we have seen were related with the shaft work output, which is W net. So what we have said that there is a Brayton cycle, and then this is TS diagram for the Brayton cycle, and then in this TS diagram this is 1 to 2 which is compressor, then 2 to 3 which is heat addition in the combustion chamber, and then 3 to 4 is the turbine, and then 4 to 1, and then we have 2 here, then it becomes 2 dash, and then we have 3 here, 4 here, then it becomes 4 dash. This is what we have seen. So this we said that WC is the compressor work, which is Cp into T2 minus T1, and WT is the turbine work, which is Cp into T3 minus T4. This is what we have seen. So we said that W net is WT minus WC. But then that means that we are interested in W net, which is a non-zero number. Since this is a non-zero number, we are interested in W net. This whole cycle is called as a shaft power cycle. Shaft power cycle. Here our interest was to get the shaft power. Our interest was mainly to get W net, which is a non-zero thing. And then that shaft power obviously would be connected to or given to a generator which will produce electricity. So till time what we worked was mainly for electricity generation, like power plant like cases. But with the lecture of today, where we are going to concentrate on other aspects of the cycle, we mean here that we are interested in the Brayton cycle based power plant, but not for electricity generation, but for propulsion, but for transportation. So, in this case W net is not our interest, or W net is rather 0. We are not going to have any W net since we are interested in the propulsion system. So, in that case we will have a, suppose a gas turbine power plant where it is inside a control volume for us. This is gas turbine power plant in which air is coming with velocity Ca, in which air is leaving with velocity Cj. Then there is pressure acting on this surface of the gas turbine, which is atmospheric pressure. So, let us call it as Pa, and then this jet over here has pressure Pj. So, what we are talking about is the propulsion based understanding for the Brayton cycle. So, propulsion based understanding for the Brayton cycle, we know that we have seen earlier that there is a compressor in which air will come, then it will go into the combustion chamber, and then from the combustion chamber it will go to the turbine. Okay. This turbine was running the compressor. But here we were having turbine to be connected to the generator also earlier. So, there was W net given to the generator, Wc was given to the compressor by the turbine, and obviously there would be some transmission losses, then in both the sides it has to give more. So, turbine has to give more work than Wc to the compressor and more work, then rest of the work it will obviously give to the generator. So, the point is here we are getting the velocity which is almost the velocity which is coming at the inlet to the compressor, since the cycle over here whatever we have drawn is drawn for the constant mass case. So, everywhere we are having same mass. Obviously, we will add fuel and then the mass of fuel is neglected. Otherwise, here we have mass of air, here we have mass of air plus mass of fuel, here we have mass of air plus mass of fuel, and here we have, obviously in case of open cycle we do not have anything, but we will again take air which is mass of air at 1. But if we have an closed cycle plant, then we will not have mass of fuel, we will not have mass of fuel, then it becomes mass of air everywhere. So, whenever we draw a TS diagram, we draw for a constant mass flow rate or a constant mass kind case. So, here the point is that we are going to leave this air. So, the velocity which is coming out from the turbine is almost equal to the velocity of the inlet to the turbine compressor. So, the point is now we are interested in having a propulsion system. Since we are interested in propulsion system, we want Cj to be the velocity of the jet to be coming out of the turbine. So, we have Ca here and we have Cj here. So, now it is going with higher kinetic energy as compared with the inlet kinetic energy. So, this change in kinetic energy or change in momentum would lead to the thrust to the power plant or to the aircraft. So, we are interested in generating the thrust in case of power plant which are used for transportation applications. Obviously, these things would actual power plant would have many components than this. It would have multiple compressors, it would have intake, and then after the turbine there are maybe there are multiple stages of the turbine, there might be afterburner in case of the turbine, but at gross it would be like Ca like here and Cj like here. So the performance cannot be judged here based upon the efficiency what we have talked about, W net upon Q in. So thermal efficiency of the Brayton cycle is not applicable if we are going to go with the plant which is going to be used for transportation application. So having said this, we need to make the new arrangement or new performance parameter for the transportation application based thermal power plant or Brayton cycle based power plant. In this case, we have actually major objectives, many objectives to decide or design a thermal power plant, Brayton cycle based gas turbine power plant. So in that case, we might have an objective to work upon maximum thrust, we might have to optimum upon we might have to work upon optimum economy in case of cruise or in case of steady flight. So these objectives need to be thought for, and then these objectives would have certain quantifications, and those quantifications need to be assessed while comparing two Brayton cycle based power plants. So first what we are going to see here is what is thrust, as what we saw earlier, that what is W net, which was required in that case. But now we are interested in thrust. So what is thrust? In this case, we define thrust as, from the Newton's law, we can find out thrust is equal to m dot into Cj minus Ca. This is the thrust. The rate of change of momentum is thrust applied or thrust gained, thrust generated by the power plant. So this is thrust. So what is thrust power? What is the power? We know that we use power concept for all the kind of engines. We say that our two-wheeler has certain HP engine, our four-wheeler has certain HP engine, there we use horsepower. So same way we are using horsepower for the gas turbine based transportation power plant. So power is, this is thrust into velocity. So what is the velocity? Velocity is Ca. This analysis is same, where basically we are at this moment considering that engine is stationary and air is coming with velocity Ca and the gas is leaving with velocity Cj. So but in real flight, what would happen? Flight will move with velocity Ca, which is Ca aircraft velocity, and jet will move with velocity Cj. So the same thing, if we change the coordinate system, then we can make the flight to be stationary, we can have the air to be entering with Ca velocity, and then the jet will move with Cj, corresponding Cj velocity. So this is the power. Now we have to define this power is to be compared with the actual input energy which was given to generate this power. So that corresponding comparison is called as propulsive efficiency. Propulsive efficiency, and propulsive efficiency is thrust power divided by input energy. So what is energy? What is input energy in this case? Input energy, change in kinetic energy between outlet and inlet. So that is change in kinetic energy, and change in kinetic energy, we know that now thrust power is m dot Cj minus Ca into Ca divided by half m dot into Cj square minus Ca square. So this we can rewrite, and we can say that m dot Ca Cj minus Ca divided by half m dot, and this we can split into Cj minus Ca into Cj plus Ca. So here Cj minus Ca will cancel, m dot will cancel, and then we get 2 Ca divided by Cj plus Ca. So we have propulsive efficiency as 2 upon 1 plus Cj upon Ca. So this is the formula for propulsive efficiency of a gas turbine power plant. Okay. So this propulsive efficiency will be judged with the between the two engines to understand which is a better engine having more propulsive power, more propulsive efficiency. So then what would happen in this case, that we can see that propulsive efficiency is 1 is basically 2 upon 1 plus Cj upon Ca. So when propulsive efficiency is maximum, this formula clearly says that propulsive efficiency is equal to 1 if Cj is equal to Ca. If Cj is equal to Ca, okay, and then propulsive efficiency is 0 if we have Ca is equal to 0. So we have two extreme cases, one, and in both the extreme cases there is no flight. When Cj is equal to Ca, propulsive efficiency is maximum, but then there is no flight taking place. And then in this case Ca is equal to 0, then that is also we will not have any flight. So these are the extreme cases which are corresponding to extreme values of propulsive efficiency. So what is actually propulsive efficiency going to decide for us? So there we have to remember a point that there are many aircrafts in the reality. We have aircrafts like we have piston prop, we have turboprop, we have turbofan, and we have turbojet, we have ramjet, and we have scramjet. So these are the different aircrafts what we can generally see in the sky or in the present situation. We have different aircrafts with us. So these different aircrafts basically have different propulsive efficiencies, and their propulsive efficiencies can be compared. So in this case propulsive efficiency is in this direction. So propulsive efficiency increases in this direction. So lowest propulsive efficiency is for scramjet, highest propulsive efficiency is for ramjet, and then turbojet, turbofan, turboprop and piston prop will have increasing propulsive efficiencies. Here what we have to understand is that the thrust over here in this case is gained by the two things. We have seen that what is the thrust. Thrust formula for us, thrust was m dot into Cj minus Ca. This was the formula for thrust. So thrust is gained by an aircraft for a given mass. It will gain the thrust by change in velocity between the inlet and outlet. So for that there are some aircrafts which will have a very large number of Cj minus Ca, very large value of Cj minus Ca. If value of Cj minus Ca is large, then obviously propulsive efficiency is decreasing. So if jet which is coming out of the aircraft is having very large velocity as compared to aircraft velocity, then those aircrafts would have lower propulsive efficiency, and then that is the case with scramjet, ramjet and turbojet. So these aircrafts, and parallelly with turbofan. So these aircrafts would have jet velocity much higher than the velocity of the aircraft or the air which is coming into the engine, and then they handle lower mass flow rate of the air as compared to the other engines. But their belief is upon, their design is upon increasing the kinetic energy more or increasing the velocity more. But then there can be one more way to increase the thrust by not changing much the Cj minus Ca, but deal with large amount of mass of air. And in this category we have turboprop and piston prop. These are propeller based aircrafts. We are going to see these aircrafts in next class, but this class is mainly upon the cycle. So we are just touching this point, that how the different engines would have different propulsive efficiencies. So these engines like turboprop and piston prop, they are driven by propeller, where propeller churns large amount of mass of air, it deals with large amount of mass of air. So what would happen is, it will have not much difference in Cj minus Ca, but it would get larger thrust. So large amount of mass of air is dealt by propeller based engines. So they have higher propulsive efficiency. But there is one more attitude to look into it, that they need large amount of mass. So they need large amount of mass, so then they cannot be traveling at larger altitudes. So they will be travel at lower altitudes. But the other engines which believe upon the larger velocity of jet, they can handle lesser amount of mass, so they can go with the higher altitudes. So this is how propulsive efficiency is going to define how the design of the engine is going to be. So in the same case, now if we go ahead and then we define that there is something like energy conversion efficiency. So energy conversion efficiency is the efficiency, energy conversion efficiency. Energy conversion efficiency is basically, we got propulsion due to change in kinetic energy. So change in K, but who helped us to change this kinetic energy? So there we had fuel. So we had some fuel burnt, and then we had some calorific value of the fuel. So we used chemical energy to change the kinetic energy. So kinetic energy change which has happened, which took place across the turbine or across the power plant, gas turbine power plant, is due to chemical energy. So change in K divided by chemical energy is the basically our energy conversion efficiency. So we have half m dot A into Cj square minus Ca square divided by m dot F into calorific value. Okay. So this is what the formula for energy conversion efficiency. Then we have next formula, which is called as overall efficiency. Overall efficiency of the power plant. So overall efficiency means we have basically different energies, and then first what we considered was propulsive efficiency. In propulsive efficiency we considered two energies. One energy we considered was thrust power with kinetic energy. In energy conversion efficiency we consider kinetic energy with chemical energy. Overall efficiency is basically power with chemical energy, which is m dot F into calorific value. So we can decompose it with power divided by change in K into change in K divided by mass of fuel into calorific value. And we know that now overall efficiency would become, this is propulsive efficiency, and then this is energy conversion efficiency. So this is the formula for overall efficiency of a power plant. So these are the aspects what they are going to define the comparison between our quantification, how to quantify and how to compare between two power plants. There is one more thing which we can use for comparison, is the specific fuel consumption. Specific fuel consumption. And specific fuel consumption is defined as mass flow rate of fuel divided by thrust power. So, mass flow rate of fuel divided by thrust. So, here we can divide by mass flow rate of air in both the case. So, this becomes F, which is fuel air ratio, and then this becomes specific thrust. So, this is how we have specific fuel consumption defined. So, specific fuel consumption is basically we have some requirement of fuel to generate unit value of the thrust. So, this is what the definition of specific fuel consumption. So, when we want higher thrust, basically we parallelly mean that we want lower specific fuel consumption. So, we want lower specific fuel consumption, we want higher propulsive power, we want higher energy conversion efficiency, we want a higher overall efficiency of a power plant. So, this is how we have defined. So, now next, using this concept of specific fuel consumption and then the concept of work ratio, we will solve an example which is not exactly related with this power plant based application, but for the application what we had earlier considered for electricity generation. So, this example deals with the fact that there is a gas turbine which has inlet temperature at 7 degree Celsius and pressure as 1 bar. This air gets compressed to 4 bar pressure using a compressor of isentropic efficiency 82%. Maximum cycle temperature or temperature at the entry to the turbine is 800 degree Celsius. Isentropic efficiency of turbine is 85%. Calorific value of the fuel is 43.1 megajoule per kg. Heat losses are 15%. And then we are given with certain standard data specific heat ratio for gas. This is a new concept which is given to us, specific heat ratio for the gas. Okay. And then we are supposed to find out what is the thermal efficiency, compressor work, heat supplied. Apart from that, we have to find out air fuel ratio, and we will also find out work ratio, and we will find out what is specific fuel consumption for the power plant. So, in this case we are again going to draw the TS diagram for the cycle. This is T, this is S. One to 2 dash, then 2, then 3, then 4 dash, and then 4. So, this is how our cycle is going. Now, what is given to us? We are given with T1 7 degrees Celsius, which is 7 plus 273 Kelvin. We are given with P1 is equal to 4 bar, P1 is equal to 1 bar. We are given with P2 is equal to 4 bar. So, we are given with Rp is equal to 4. We are told that compressor efficiency, which is isentropic efficiency of compressor, is 0.82. We have been given that T3 is equal to 800 plus 273 Kelvin, and then we are given that turbine isentropic efficiency is 0.85. We have calorific value of fuel is 43.1 megajoule per kg. Here one point we have to remember, this megajoule per kg is per kg of fuel. So, we mean here that 1 kg of fuel, if it is burnt in air, we get 43.1 megajoule of energy. So, this is not per kg of air. Okay. So, this point to be remembered. Then there is loss of heat in the combustion chamber is 15%. And these are the things which are given to us. Okay. We are parallelly given that gamma for air is 1.4 and gamma for gas is 1.33. here we have to keep one point in mind. Here in this section we use gamma for air, in this section we use gamma for gas, and in this section we use gamma for gas. Since air is getting compressed in the compressor, so we should use compressor with air as working medium, so we have gamma air. But in the combustion chamber we are burning the air with the fuel, so we have gas, which is a combustion product, and that gas gamma is 1.33. And then in turbine we don't have air, it is the gas which is expanded, so we have gamma gas to be used in these sections. There is one more thing which we could have used as m dot f plus m dot a here, m dot a plus m dot f here, and only m dot a here, but that m dot f would be negligible in comparison with m dot a, so we used only m dot a everywhere. Having said that, we can quickly find out compressor work, where Wc is equal to, we know that Wc dash, which is ideal, which is Cp into T2 dash minus T1. So we can know T2 dash, from Rp, where T2 dash upon T1 is equal to Rp raised to gamma minus 1 upon gamma, where Rp is given to us, T1 is known to us, so T2 dash can be found out. Then we can use compressor efficiency formula, which is Wc dash upon W. So this is ideal compressor work divided by actual compressor work. Using this formula we can find out Wc, since we would know Wc dash and we know eta C, which is compressor efficiency. So first thing is done. Then we want to find out what is heat supplied. Heat supplied is simple. Here Q is equal to Cp into, we are given with Cp gas also, we are given with Cp gas T3 minus T2. So we know T2 from the, we could find out rather T2. Here Wc can be also find out as Cp into T2 minus T1, but in this case we need to find out T2. So for T2 we used formula as T2 dash minus T1 divided by T2 minus T1. So here T2 dash would be found out from T2 dash upon T1 and Rp raised to gamma minus 1 upon gamma. So Rp is known, T1 is known, gamma for air will be used, then we can find out T2 dash. T2 dash will be put over here, T1 is known, compressor efficiency is known, T2 can be found out, and then that's way we can find out compressor work, or otherwise we could have found out in this way from T2 dash and compressor efficiency. But now if we go by this way we would know what is T2. So T2 is known, T3 is given, Cp of gas is given, here we have to use Cp of gas, we can find out Q in, that is the actual heat which is going into the gas turbine power plant. Then we can find out turbine work. So for that obviously we have to use Rp. So Rp usage will give us T4 dash upon T3. Basically we know that T3 upon T4 dash is equal to Rp raised to gamma minus 1 upon gamma. We can find out T4 dash, and once T4 dash is found out we can use turbine efficiency formula, which is T4 minus T1 divided by T4 dash minus T1. So this T4 is known, T1 is known, turbine efficiency is known, we can find out T4. Once T4 is known we can find out turbine work as Cp into T4 minus T1, and this T4 is obtained from turbine efficiency, but this Cp is Cp for gas. Again this has to be remembered. So using this we can find out W net, which is turbine work minus compressor work. Okay, and then we need to find out what is the thermal efficiency, and this is a little tricky. So here thermal efficiency of the plant is W net upon Q in, but for Q in we have a problem that the Q in what we calculated here, this Q is the Q, which is actually received, but Q in is supplied energy, and this is supplied more since there are losses of 15%. So, this is W net upon Q divided by 0.85. Okay. So, this is like, this would increase basically Q by dividing the losses. Basically, this can be also treated as combustion chamber efficiency. So, Q in is actual received, Q is actually received Q, but Q in is practically the chemical energy which was available, only 85% was received. So, basically 0.85 is equal to Q upon Q in. Okay. And then that would help us in finding out what is the thermal efficiency of the cycle. Now, major objective is to find out air fuel ratio. So, what is air fuel ratio? Air fuel ratio is to apply the energy conservation equation in the 2-3 case. So, if we apply energy conservation, then mass of fuel is burnt and then has released calorific value, amount of energy, and it was used to heat mass of air into mass of fuel. Okay, mass of air from T3 minus T2, but only 0.85% was used. So, it is 85% was used. So, this is like this. So, here we know calorific value, we know this efficiency which is combustion chamber efficiency, we know T3, we know T2. Then we can divide everywhere by mass of air, and then 0.85 into F, which is mass of fuel upon mass of air, which is fuel air ratio into calorific value, is equal to 1 plus F into T3 minus T2. And that is how we can find out fuel air ratio, or 1 upon F is air fuel ratio can be found out. Everything is known to us. Now we have our formula of SFC, specific fuel consumption, and then we found that it is F divided by W net. So, this F divided by W net, but this W net has to be specific work output, thrust power. We have seen that if it is a thrust power, then W net will come into picture. Okay. So, this is specific fuel consumption of the power plant, which is basically used for the electricity generation, but similarly if we would have the gas turbine based power plant for electricity generation, then this is the thrust power, this is F. Okay. So, but generally it is having unit of mass of fuel, it is having unit of mass of fuel divided by the thrust power. So, it has unit of kg per second divided by kilowatt. Okay. But it is represented as kg per hour also. So, we have to multiply by 3600 to get kg per hour per kilowatt. So, that is how per kg of air. Okay. So, this is how we have the basically the specific fuel consumption to be found out. Okay. So, here we end the basically our discussion on some aspects of the cycle. In the next class we will see about the details of the different power plants which are used for the electricity, which are used for the propulsion applications. The discussion which we have continued or which we touched for the propulsive efficiency, those engines, aircraft engines will be seen in the detail in next class. Thank you.